Hey, Math 30-1s, we're going to go over our released items for our permutations combinations to help you prepare for the exam next week or test next week. For the stuff is really only just on permutation combinations. I won't have any binomial theorem stuff on there. Don't worry about that. Those nice little optional videos you see for that week. We're not going to get tested on that. It's just kind of fun information. There is some more math behind it. If you want to delve in a little bit deeper for that, that's your prerogative. That's what you're going to do. So you might see that a little bit more in calculus and stuff. So if you do plan to go into calculus, just research binomial theorem, Khan Academy and stuff like that. You have a whole summer to plan that out, right? It's not the hardest subject in the world, so I'm not too worried about that. You'll figure it out if you're going that route anyway. So let's go through some of these, and then you can see it's quite mixed, an array of questions here. We got 11 pages. So let's try this out. Okay. So prior to 2010, standard license plate consisted of 3 letters followed by 3 digits. You can see here in Ontario consists of 4 letters and 3 digits. They could be repeated. There's 23 letters in the alphabet that could be used. They're probably trying to avoid using things that look like other letters or numbers, like zeros look like O's and ones, and I's look the same. Q's and O's look the same as well. All the digits from 0 to 9 may be used. And let's check. Okay, so how many? Has how many times greater? So because it has an extra letter in it, how many times greater is it? Well, it's pretty simple to think of that. It's really just going to be 23 times greater. But let's go through. Yeah, I don't even know why we bother. It's 23 times because there's this extra letter. So if I were to do the Ontario, it'd be 23 times 23 times 23 times 23 because the letters can be repeated, right? Letters and number digits can be repeated. So I can do like that. So I'd have 23 times 23 times 23 times 23. So this is the Ontario plates, right? There's going to be more of them because there's more choices. And then I'm going to have 0 to 9. So it's 10, 10, 10. Okay, so I'm not actually going to find that number out because I'm going to divide by Alberta. Because that's just how you figure out how many times greater things are. You just divide them. And then you start reducing things off. You're like, oh, they both have 3 23s. They both have 3 10s. Sweet. The only thing that's left over is 23. So 23 times greater. The number. Oh, this is a different question altogether. Is that it? Yeah, okay. The number of 4-digit and 5-digit personal PIN numbers that can be formed. It says or, so that's a big key. I'm going to add 2 things together. You've got 2 different cases. Using only digits, so there's no 0, so I don't have to worry about starting something off with 0. No repetition. Okay, key, no repetition within a single PIN. Okay, so 4 digits. Pretty easy. 1, 2, 3, 4, 5, 6. 6, 5, 4, and 3. I could have wrote that as 6P4. Right? You can do that, or you can do it that way. And then if I have a 5-digit number, I have 1 extra piece here. So see, that's going to be 2 times greater, really. So this would be 6P5. Cool. Okay, so we're going to get 2 numbers here. 6, 8, 4. So you get 360. I'm hoping the next one's going to be 720. Hopefully it is. Hey, it's 720. Okay. It only has 2 times more than the previous one. So, and then because there's an or, because it's or, I'm going to add them together. And you get 1080. Nice. There you go. In a local high school, a group of 16 students comprises 7 singers, 9 actors. It's a 6-person executive council selected. So it doesn't look like there's any positions to this council. It's just we have that. And I want at least 4 actors in this one. Okay. So it's 16 in total. Okay, so I want at least 4 actors. Ooh, this is going to be interesting. At least 4. Oh, 6-person council. Okay. So we have 9 actors. I want 4, or 9 actors and 5, and 9 actors or 6. Those are my only 3 cases I can actually have here, right? Because I have to go up to 6. Yeah, I thought there'd be more because you can go up to 9, but nope. And then we have 7 singers. So if I had 7, I would have 2 singers to fill out that council. I have 1 singer to fill out this council. I have 0 singers to fill that council out. Okay. Then we're going to find all of these numbers. So a little bit of extra work here. Let's see. 9C4, 126. 9C5, 126, which makes sense. 9C6, 84. Okay, so I did this, the 9s. And again, the 7C, that's 1. 7C, this is 7. And 7C2, I don't know that one. Okay. 21. Okay. So 84, 126 times 7, 882. Oh, so it's just crossed off A already because of that. And 21. So 2,000. I'm just going to cross off B because that's this number right here. And I'm going to add in these other pieces. So that plus 84 plus 882. Okay, so it ended up being D in this situation. Cool. For a particular 4-digit bank code, the first and last digits must be odd, and the second digit cannot be a 4. Digits cannot be used more than once. To determine the total number using the fundamental counting principle, what numbers would I put in those spots? Ooh, this is a tricky question. Okay, so the first and last digit has to be odd. So we go from cannot be 4. This is a bank code. It doesn't say a number, so I'm assuming that we could have a 0 in there. So there's 10 numbers in total from 0 to 9. 5 are odd. 5 are even. Okay. So if I'm going to put a number in here, it says can total different must be digits cannot be used more than once. So I can't repeat anything. So if I put a 5 in A, there's more than one because I put a 5 in D as well. But if I put a 5 in A, that means I would have 4 choices for this last digit. Okay. So I've used 2 digits up so far. So now I have 8 digits in total, but I can't use a 4 here. Okay. So if I can't use a 4 there, then I only have 7 digits to play with. But then I can use a 4 in the second spot if I wanted to. Right? There's a lot of weird restrictions. Yeah, okay. So I put another 7 there. There you go. So it'd be 5, 7, 7, 4, or 4, 7, 7, 5. Because you could have went the last digit first. Yeah, that looks good. I think that's the only way you can do that one. For a picture, 3 boys, 3 girls, arranged such a way that girls and boys alternate the number of different arrangements that we can actually have. So 1, 2, 3, 4, 5, 6. I'm going to have 3, 2, 1. So those are the girls, right? Or boys, doesn't really matter. And then I'd have 3, 2, 1. I can see what they're going at here. Like if I did this one right now, I'd get 36, right? But what if I did it this way? Right? I'd get another 36. I'm going to get 72 in this question. 3, 2, 1, 3, 2, 1. My legend here is the box are girls and the line are boys. Okay. So I can either start with the girl or start with the boy. So I got these 2 situations. It's that or this. And you get that. Cool. The number of 6-letter arrangements. Just make sure I started the video. The number of 6-letter arrangements that can be used from the word verify if letters E and R have to be next to each other, but not necessarily in that order, so that means they can be the other way around, is, so if I treat E and R as one letter, 6, there are 5 factorial ways to do that. If ER are one letter, right? Then I can times this by 2 factorial, and then I get my final answer, because I can switch the order, right, between the two. So 5 times 4 times 2. Okay, so times it by 2, I get 240. All right, I'm not going to go too much depth on how to figure that one out. That's just like a two-headed monster question. There's no repetition, is there? No repetition. Well, a physical education teacher in a high school is made of a schedule of 15 intramural teams in the school. Decide to split the teams into 3 divisions of 5 teams each. Each player must play each of the other teams in the division once. Teams in a division do not play against other teams in another division. So there's no crossover here. So how many games in total are there? 3 divisions, 5 teams. Okay, so I'm just going to do it for one division right now. So to figure out how many games you're going to have to do is going to be 5C2. Now, order doesn't matter. It doesn't matter if one team plays the other or the other team plays this one. So it doesn't matter how you pick the teams. They're just going to play against each other. But there has to be 2 teams to play against each other. So that's why it's a 5C2 situation. Now, there's other questions like handshake questions, very similar to these kind of questions, where they might ask for handshakes. Like, how many handshakes are there? It would be the same idea. You need 2 people to have a handshake. So 5C2, 10. So there's 10 games in each division, okay? Because each one is going to get 5 teams. So there's 30 times by 3, and I get my 30 there. Cool. I like that kind of question, that handshake kind of question. Maybe mention that. Just double check out that question there. If a committee of 3 is selected from a group of 15 and 16 teachers, 15 students and 6 teachers then. Ooh, at most 1 teacher. Okay, so at most 1 teacher. Committee of 3. So at most 1 teacher. I'm not going to have any more, but I can have no teachers. That's good. Okay, so let's go 6C1 and 6C0. Can't go anymore. Okay. But then oops, sorry, I'm not going to do that. You have to multiply them because you need the students in the committees as well. So 15C2 to fill out the committee, and then 15C3 to fill out that committee too. 15C3 is 455. And 15, yeah, I thought maybe at my calculator we get a beard. I didn't. Or mustache. Oops. Poop, poop, poop. Bunch of. Okay, 15. C2. So 105 here times the 6. So 630 plus the 455. 1,085. Yeah, I can see that, why that's there. Okay. Cool. Darren, 2-year-old Darren is playing with a train set. Engines are detachable from the cars. Letters are glued so they can't move them. That's good. And there are 2 cars with the letter R that are identical, so Darren doesn't know how to spell his name, which is typical of a 2-year-old, I guess. But he does know the engine has to start at the front. Smart kid. Determine the number of possible arrangements he can have with the engine in the front. Okay. So really, I'm just going to get rid of that piece because that's just going to be a 1. This has to be a D here. But everything else can be rearranged 5 factorial ways, but there are 2 R's. So I'm going to have to divide this by 2 factorial. 2 R's. Okay. So whatever 5 factorial happens to be, which I did before, I think it's 120, right? It seems like if you do it enough, you'll figure it out. So that's 60 in total. So it's going to be 1 times 60. It's going to be 60. I don't know why I bothered with 1 times 60. Okay. So 60 different arrangements. Eventually, you'll spell his name correctly one of those times. So in the diagram shows a website chart. The seats that are being reserved are in black, and the lighter ones are available. And there are 12 seats available here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yep. There are 7 customers. How many ways could they arrange in those seats? So, different number of ways. So I have 12 seats. I want to pick 7 of them. I think it's going to be a C situation here. How many different ways could you arrange? Yeah, I would say order kind of matters a little bit because some seats might be more desirable than others. Yeah. Okay. Yeah, so I would say it's definitely a 12P7. Of all the letters in the word diploma, how many different arrangements are possible if it must begin and end with the I, O, or an A? Okay. Now this is an or situation, but we can just simplify this down. Okay, so how many letters? 1, 2, 3, 4, 5, 6, 7, 7. All the letters are different. Makes sense. Okay. 7 letters. We got 3, 2. Yeah, because it's 3. Yeah, makes sense. 3 and 2, and then we have all the other letters in here. So 5, 4, 3, 2, 1. I don't know why I wrote that all out. That's just 5 factorial. So let's see. Cool. Yeah, so most of the time when they talk about letters of words like this, we want to use them once. It doesn't specify that though. Okay. Josh wants to rent a car. He's narrowed his choices to a sedan, a compact, and economy car. The colors are black, red, and white. He must choose between standard and automatic. So this is a pretty simple question. He has 3 choices for the type of car. He has 3 choices for the color, and he has 2 choices for that. So that's going to be 9 times 2. It's going to be 18 in total. So 18 different kind of cars you can look at there. Not too bad. Identification code on the bank consists of 1 digit followed by 2 letters. The code must meet the conditions. Okay, the digit must be odd. Okay, so we have 5 choices for that one. Okay, the letters 1, 2, 3, 4, 5 letters cannot be used. So there's only 20 letters left in the alphabet because there's 25 letters in the alphabet, right? Or is it 26? I can never remember. Oh, it's probably 26. I'm probably. What was I thinking? Yeah, I'm 7 on here. Yeah, there's 26. What was I thinking? Apparently, I just don't know the English pretty well here. So 21. So checked out those letters, but you can't repeat. Letters cannot be used more than once, so I had to just go down by 1 there. So whatever 5 times 21 times 20 happens to be, 2,100 different combinations can be created, or bank card combos. Cool. A volleyball team is made up of 6 players standing in a line facing the camera for a picture. That Jonah and Emily must be together, and the expression could be what? That's a good question. Okay, so picture. So it's going to be a permutation. I'm going to cross those 2 off. I'm going to say it's A. So what they're trying to do here, they're trying to treat the Emily and Joan as like a 2-headed monster. So if they're stuck together, there's really only 5 players then. You have this person, then you have 1, 2, 3, 4. So you have something like this. Okay. So there's 5 of these. So this is 5 factorial. 5 factorial is just the same as saying I have 5 and I want to pick all of them. And order matters. But there's 2 ways to rearrange those 2 heads. So that's why it's A in this situation. Oh, I don't give you very much space. There's A, B, C. There's 3 different questions here. Determine the number. All the letters are used in the word excesses. So 2 E's, 3 S's, and 2 C's. 1, 2, 3, 6, 7, 8. Yeah, there's 8 letters. Oh, that's kind of fun. How many of these arrangements begin with at least 2 S's or begin with exactly 2 S's? Now, this is a very weird question. Okay, I like this question. Okay, so A could either have 2 S's or 3 S's in the beginning. At least? Yeah, at least 2 S's or 3 S's. So I have 2 situations here where I have 2 S's or 3 S's. What I'm going to do is I'm going to solve for B first. Exactly 2. And then I'm going to add on that extra piece because the exactly 2 for B is going to be plus I'm going to have to divide all the repetition. How many letters? 8. 1, 2, 6, 7, 8. Okay. So I have 3 S's. I have 2 S's, and then I have, but I have to be exactly. So now the problem is this next letter cannot be an S, right? It's got to be something else. And then all the other ones could be an S somewhere. It has to be exactly 2. So this cannot be an S. Not a S. Well, that's horrible. I'll fix this. Okay. You can see my computer slowly dying on me. Not a S. Right in there. Okay. So how many other letters do I have? So I have 1, 2, 3. So it's 5 choices here. I can have 5 other choices for this one, not an S. But then all the other ones could be 5, 4, 3, 2, 1. Right? It could be anything else. Okay. Then what I'm going to do is I'm going to divide this by my repetition. So I have 2 C's. I have 3 S's. I have 2 E's. How many letters is that? 1, 2, 3, 4. 7 of my 8. Yeah, okay, makes sense. And just times them all together. So 5 times 4 times 3 times 2 times 1. I want to put that in there. Okay. Divide by, oops, 4 times 6. There's 150 ways for the exactly 2 S's there. But A can have at least 2 S's there, right? Begin with at least 2. So I got 2 or 3. So I'm not going to explain why they're different, right? Because this is just going to explain it. Like this has to have exactly 2, right? And this one cannot be an S, okay? And then this one will be 2 or 3. So I already have the 2. So this one is already 150. I already know that one. Or I can have the 3, 2, 1. That's all the S's. And then I would have 5 more factorial? Yeah, 5 factorial all the way down. So 6 times 5 factorial. Which is, oh, and then I divide. Sorry, I forgot to divide all that. I'm going to divide by the 2 factorial, 3 factorial, 2 factorial as well. So that's going to be divided by 6 times 4 again. So this is only 30 ways. So if I add those together, because or means plus, you get 180 ways. Cool. At a local dealership, the manager wants to line up 10 cars in the same model in the parking lot. There are 3 reds, 2 blues, and 5 greens. Ooh, okay, there's repetition. They're all the same model. So we have to divide that out. But the blue cars cannot be together. Ooh, that's good. So I want to find out 2 things. I'm going to subtract them. I'm going to find out how many ways can I rearrange all 10 cars. That's it. Just the 10 cars. Just rearrange them. So I can rearrange all 10 cars 10 factorial ways, but I need to divide out the repetition. Okay, so this will end up being 10 factorial divided by 6 times 2 times whatever 5 factorial is again. That's 120, right? So there's 25, 20 ways of all the cars, right? And what I'm going to do is I'm going to subtract out the cars when they're together. Okay, so we still have to divide out the repetition part. So that's just going to be here. I guess I could have done that just because it's a common denominator. Could have done that after the fact. But they're going to be together because I can treat all the blue cars as 1. 9 factorial ways. Times, because I can move the cars either way, because I gotta put that in there because I've included it as part of my repetition on the bottom. If I didn't, I could just treat that as 1 car and just kind of got rid of the bottom one too. But I'm gonna have to do that. Okay. So 9 factorial divided by 6 times 120 as well. So there's only 504 of them together. So this here is together. So I'm going to take the 25, 20, and minus them together. And I get 2016. There you go. Yeah, I'm sure there's other ways to go about that one, but that's the way I would do this one. 14 different fruits. So make sure I'm in the right spot here. Where am I? Oh, I'm on page 8. Okay, I'm doing pretty good. Okay. 14 different types of fruits are available. How many different fruit salads can be made? Exactly 5 types of fruits. Okay. They're going to be in a fruit salad. They're going to be chopped up. So I'm not suggesting permutations. Bad idea, right? Because of the P. All right. 14 choose 9 will work because the only reason this works is because that is the same as 14 choose 5, because the 5 plus 9 ends up being 14. So remember, that's the same as this example with the books, right? If I choose 2 books, that's taken off the table. That leaves behind 3. So I could put those in the salad or something. So 3 is definitely a good one. All right. I'm going to get rid of Jackie here because order does not matter. That means order does matter. Plus that would be only 5 fruits. It's totally wrong anyway. 14C. Yeah, this is too many. This is choosing all of the fruits and then getting rid of 5 of them. That'd be like having 9 fruits altogether. So that's too many as well. So it's definitely going to be this one because that's the same as writing 14C5 as well. So cool. At a meeting, every person has to shake hands with another person. So that means bump elbows or I don't even know what's the best way to do. Nod your head at somebody. Okay. There are 36 handshakes in total. So that means I don't know how many people are there, but I do know that there's 36. And order doesn't matter. Whoever initiates it, doesn't matter who initiates it. All right. You're just going to shake hands anyway. So there's going to be n factorial divided by n minus 2 factorial 2 factorial. That's just the formula. I'm going to times that 2 factorial up to the other side. So I get 72 over here. And then I'm just going to expand out that n factorial. So n times n minus 1 times n minus 2 factorial. You could have just guessed early, honestly, but if this was like a written response question or something, you'd want to write it all out anyway. So make it equal to 0. What two numbers multiply out to 72 and add to -1? My mental math, this is stuck in my beard, or mustache apparently. Okay, so let's divide this by 6. No, 62. Okay, 8. There, 8 and 9. Okay, so 8 and 9, n minus 9, n plus 9. It's got to add to a negative number, so there's 9 people at this meeting. There you go. And you can double check that. 9C2. 9. Yeah, 36. Cool. 6 people have been created to create a group from 8 doctors and 40 nurses, a 6-person health committee, sorry. The expression, the total number of councils that contain at most 2 doctors. That means I can have 2 doctors. Oh, at most, I can have 2 doctors, 1 doctor, or 0 doctors. Okay, so I can have no doctors as well. So I do like, first I'm going to cross off the P's because this is just a council. There's no positions in this council as far as I know, so I'm going to cross those off. But I like B because it includes the 8C0. 8C0 is not 0, it's 1, right? 8C0 is equal to 1. So I need this in here somewhere. That just happens to be here where this 6 nurses are. Okay. That's what's happening here. I think they got rid of that piece because they, 8C0 must be 0. No, that's 1. How many different 4-letter arrangements are possible using any 2 letters from the word smile and any 2 letters from the word frog? Okay, so this is an interesting question. So this involves both permutations and combinations. You're going to take 2 letters from each, got them in your hand, and then you're going to take those and then put them in order. So first of all, I want to know how many letters, combinations can I get from the word smile? So I have 5 letters. I'm going to choose 2 of them. There's 10 ways I can choose letters from that. And there are 4 letters. I want to choose 2 from frog. This is from frog. This one I can't remember this one. 6. Okay, 6 ways I can do that. Okay, so there's 60 different letter combinations I have, and all the letters are unique here. So 10 times 6, 60 letter combinations of letters. But I can now rearrange those letters. I've got 60 letters, different ways I can get letters, but each of those combinations, I can put them in different ways, right? So I'm going to times this by 4 factorial. And get 144. Okay, cool. All right, for a photo, 9 volleyball players stand in line. They will place the shortest player one end, one of the 2 ends, the tallest player in the middle, one of the 2 ends, right? So that's going to be a situation, 1 on the left, 1 on the right. So I got to worry about that. We have 9 people. 1, 2, 3, 4, 5, 6, 7, 8, 9. So right in the middle, I have one choice. The tallest player has to be there. But I could either put the shortest person on this side, or it's going to be the same calculation both ways. I could put the shortest person on this side. So I'm just going to do it once and then times it by 2. Okay. So the rest of the people, though, are going to be 7. 7 factorial. 7, 6, 5, 4, 3, 2, 1. So this is just 7 factorial. And this is also just 7 factorial, right? Because it's just simply the same thing. So whatever 7 factorial times 2 is. Check this. Times 2. Oh, poop. Well, it's going to be 10,080. There you go. Cool. I don't know how you got these bigger ones over here, but that's the way I would do that one. Pretty good. How many polygons can be created that have at most 4 sides in this situation? So a polygon created is just by picking points and then connecting the dots, right? So at most 4 sides, polygons can be created here. So if I pick these 4 points, it doesn't matter the order I pick them, it's going to be the same point. Okay, so it's going to be a combination question. 3 or more sides by connecting the points with straight lines. Yeah. If I pick 2 dots, I don't have a polynomial. I have to have 3 dots, right? And if I have 4 dots, I have 4 sides. Okay, so at most 4. So I'm going to go, because I have the 2. So I got the 4 sides and the 3 sides. So I have 6C3 or 6C4. Okay? I'm just going to add them together because it's an or. 20 cross cross. Okay, so there's 20 ways to get triangles. 20, sorry. And then 15 ways to get that and add those together. Get to 35 ways to do that. Pretty cool. Where am I? Second last page. Nice. Okay. Students in the math class are creating and exchanging encoded messages with a partner. Cool. Given that there are 630 different pairs of students possible, algebraically determine the number of students in the math class. Okay, so pairs. So they're exchanging with each other. So I'm going to have n C2, so like the handshake question, is equal to 630. So we did this one already, so or at least some of the simplification part already. So this is what it looks like. I times the 2 up on this side, so I get 1260 on that side. And then I'm going to start expanding this one out. And I'm going to divide by factorial, cross off, cross off. So n squared minus n is equal to 1260. This is algebraically do this, so this is my algebraic method. And then what multiplies out to 1260 and adds to 1, or negative 1 in this case. Ooh, I don't know. Oh, 36, I just got to guess, 36 and 35. Pretty nice, okay. So that's going to factor out to n minus 36 and n plus 35. It's going to add to the negative, so that's why the negative number is bigger. So 0, so my n is 36. And there's negative 35 too, but having negative 35 kids in class doesn't make sense. Plus negative numbers don't work in combination like this. Cool. This is 3 marks. I don't know what exactly the 3 marks would be in this situation. I'd give 2 marks or so. Okay, students asked to encode the word factor by replacing each letter in the word with a different math symbol. There are 10 math symbols. The student creates a key, a list of the letter symbol replacements. Okay, which makes sense. Okay. And gives it to his partner to decode the word. Explain how you would determine the number of possible keys that you can create this. Now, it's got to be different math symbols, right? Can't have the same, like a times sign for those 2 letters. And it says explain and then determine. Now, hopefully you'll see me talking here. Okay, so I would say that I'm sure there's a bunch of different ways you can do this question. But the way I would approach this question would be, I have 6 letters. Now the question is like, is he creating a key? Or he's just creating a key for these 6 letters. Okay, that makes sense. Okay, they can't create a key for the whole alphabet because we don't have 26 letters or symbols. We have 26 letters, but we don't have 26 symbols. Okay, so when I think about this, it's thinking, okay, how many different options does he have for the letter F? Well, he starts off with 10 options for that, right? That's for the letter F. And then he's already used one of his options up. Then we got 9, then we got 8, then we got 7, then we got 6, right? So that's the way I would approach this question if I were to do that, because each one of his next letters has one less option. 6, 7, 8, 9, 10. So he would have 30,240 different keys he can create. He's obviously not going to do that. He's just going to create one key and do it. This would be the same as saying 1, 2, 3, 4, 5, 10 P5. You have 10 things, you got to pick 5 different symbols. Oh. Why did I say 5? Didn't I say already that there's 6? The word factor, there should be a 6 here, so there should be a 5 at the end here. So I times this by 5. Okay, so this should be the same as 10P6. I said that before, there are 6 letters, which would be 151,200 keys. Cool. That's the end. All right, cool. And then we'll see you. Yeah, I don't know. I'll see you in the next video. I was really thinking about that. All right, bye.